In this world, there exist superhumans, people who can do some pretty amazing stuff. There are the world's strongest men who can lift massive amounts of weight. There are people who are very tolerant of extreme cold, and other humans who can run incredibly fast. You get the picture. And while it may be hard to imagine that microscopic organisms could be supermicrobes of sort, it's very true. These supermicrobes are one key to finding life on other planets and the topic of this lesson. The real term for the supermicrobes I mentioned is extremophiles, organisms that can live in extreme environments. These extremophiles are not some sort of alien life form, although there may be extremophiles on alien planets. Extremophiles live right here on Earth, but they live in some pretty terrible conditions. Some live in very salty environments, others in really hot conditions, really cold ones, or deep inside solid rock. Because we know that such organisms are possible on Earth, it gives us hope that one similar to them can live in extreme conditions on other celestial objects. To have the best chance of finding a life form on another planet, be it in our solar system or planets much farther away, we need to look for evidence of water. Based on our best understanding of the basics of life, liquid water is necessary for carbon-based life to exist. That's why life developed in oceans on Earth far before it ever developed on land. If we search within our solar system for such evidence of water, we can begin to eliminate a bunch of places where life is unlikely to be. To see which celestial object in our solar system can sustain this, let's get on board a spaceship and take a tour of our solar system. First, we fly by Mercury. Mercury, like our moon, has no air and thus water would boil away into space. Too bad. Let's head on over to Venus. Venus is too hot for liquid water to be on its surface. Bummer. Let's skip Earth and Mars for now and head on over to the Jovian planets. The Jovian planets include Jupiter, Saturn, Uranus, and Neptune. The Jovian planets don't have solid surfaces for oceans to form, even if they have isolated liquid droplets of water in their atmosphere. Scientists believe such large bodies of liquid water are necessary for nutrients, chemicals, and other molecules to interact sufficiently enough to form and sustain life. What does this leave us with in our solar system then? The planet Mars, the fourth planet from the Sun, and perhaps a moon or two of the Jovian planets. Since our spacecraft is near the Jovian planets already, our spaceship swings by one of Jupiter's moons, Europa, before heading back over to check out Mars on our way back to Earth. Europa seems to have a liquid water ocean below an icy crust, sort of like how you can go to the Arctic Circle, dive underneath the thick ice, but still be in liquid water. It could be that minerals are dissolved in this water, minerals that are necessary for life. The only problem is that it may be that Europa was frozen solid at some point in its history, and this might have killed off any living organisms in it, although there's always hope for extremophiles that did manage to survive. While other moons of Saturn and Jupiter may hold some promise of life, it is really Mars that seems to be the most likely place for life to exist in our very own solar system, besides Earth, of course. So let's get over there. As another lesson on Mars pointed out, there's a lot of evidence that liquid water did at one point flow on its surface. However, the most recent soil samples from Mars have not been encouraging with respect to evidence of life there now or in the past. That being said, we've literally just barely scratched the surface of Mars. This is actually encouraging because the best chance for life to exist on Mars might be below ground, where liquid water might still run and where life would be protected from the sun's UV radiation. So, could there be life outside of our solar system on other planets? Perhaps, but the conditions for this would have to be just right. First, the stars that would have to support such life would have to be singular and not in a binary system. This is because in many binary star systems, the planetary orbits would be too unstable to support life. Half of the stars in our galaxy are part of a binary system, rendering them unlikely to support life. Many stars simply don't last long enough to support life. If we assume, based on what happened on Earth, it takes about 1 billion years for life forms to emerge on a planet, then massive stars that only live for a few million years would be ruled out as well. This means main sequence stars of type G, K, and some M stars are the best candidates to sustain life on planets orbiting around them. Also, the distance a planet is located from the type of star it orbits has to be just right. This is known as the habitable zone, a region around a star where a planet having the same approximate size and atmospheric composition as Earth would have a surface temperature that allows for water to exist. Earth is right in the middle of our sun's habitable zone. We got pretty lucky. While not impossible, the chances that all the conditions for life are met in places far away are pretty slim. So it's best we just set our spaceship back down on our homely planet for now and review what we've learned on our little trip. On our planet, we have extremophiles, organisms that can live in extreme environments. The fact that they can live in a wide variety of conditions deadly to human life gives us hope that similar organisms can live in extreme conditions beyond Earth. The best chance of finding carbon-based life depends on finding liquid water that can sustain the development of such life. This rules out Mercury, Venus, our moon, and the Jovian planets for many different reasons. The Jovian planets include Jupiter, Saturn, Uranus, and Neptune. But the planet Mars, the fourth planet from the Sun, and one of Jupiter's moons, Europa, might have some hope for sustaining life due to the possible presence of liquid water beneath their respective surfaces. Life outside our solar system would depend on finding stars of just the right size and planets at just the right distance for liquid water to form. When I mean the right distance, I'm of course talking about the habitable zone, a region around a star where a planet having the same approximate size and atmospheric composition as Earth would have a surface temperature that allows for water to exist. While coming across such a scenario isn't impossible, it's unlikely.